Okay, for the next little review problem we have to do, let's do the electric field inside and outside a long cylinder of charge with radius r and uniform charge density rho. So this is similar to doing the review of the spherical insulator, except now it's a cylindrical insulator. So we're going to start with an insulator with charge density of volume charge density rho equals charge over volume. So if you're finding the charge on this one, you do density times volume, and the volume of a cylinder would be pi r squared times the length. We're going to try and find the electric field inside and outside. Since it's an insulator, we're going to have a uniform charge distribution, just like we did with our sphere. If you looked at the review problem for the sphere, maybe you didn't, maybe you skipped right to the insulator, or right to the cylinder. So when we have an insulator, those charges are not free to move, they're stuck in place. We're trying to find the electric field in two places, inside and outside. We're going to have to draw Gaussian surfaces. So since we want the field in two places, I'm going to draw two Gaussian surfaces. Okay, here's my cylinder. If I want to find the electric field inside, then I'll do a Gaussian surface inside. My Gaussian surface should match the geometry of my problem. So my Gaussian surface is going to be a cylinder, which is inside my insulator. So that's got radius little r and length L. If I'm trying to find the electric field outside my cylinder, I'll draw my cylinder. Now my Gaussian surface is going to be a cylinder outside. For simplicity's sake, I'm going to give it the same length L, same symbol for the radius, lowercase r. So for this one, I want to find E of r less than r. This one, I want to find E of r greater than r, and I anticipate that that'll be continuous at the surface. It'll have the same value. I'm going to apply Gauss's law here. Gauss's law says that the net electric flux is the integral of E dot dA, which is equal to the charge enclosed over epsilon naught. For both Gaussian surfaces, they're both cylinders, so this part of the equation, the E dot dA, that's going to be the same for both. So I'm just going to do the one calculation there to cover both of them. The integral of E dot dA is equal to the integral of E times dA times the cosine of the angle between E and dA. For a cylinder, we've got radial symmetry with our electric field, so it comes out in all directions. Likewise over here. Okay, that picture's all right. So the blue arrows are showing the electric field. The direction of my area vector, different for the different places on my Gaussian surface. The side of my Gaussian surface, on the tube part, it sticks straight out, parallel to the electric field. On the top, it sticks straight up, and on the bottom, it sticks straight down. So the top and bottom have no electric flux because those two things are perpendicular. Same thing is true over here. So we only have the flux through the sides of the cylinders that have a contribution, no flux through the top and bottom. So cosine 0 equals E times dA times 1. Your electric field, as long as we're a uniform distance away from the center, your electric field will be uniform. E times dA, the integral of dA is A, where A is the area of your Gaussian cylinder, which is 2 pi r times the length. We'll just put in brackets, no flux through top and bottom. Okay, so now let's go through these two special cases. So when we're inside the cylinder, only a fraction of the charge is inside our Gaussian surface. The amount of charge that's inside the Gaussian surface is equal to the density times the volume of the Gaussian surface. The density has the symbol rho. The volume is pi r squared times the length. So there's the charge enclosed when we're inside our insulator. Okay, so my net electric flux is E dot dA. That's E times 2 pi RL. That's equal to my Q enclosed, density times pi r squared L divided by epsilon naught. Let's see what cancels. Pi cancels, one of the r's cancels, and L cancels. So then my electric field E is the density times R over 2 times epsilon naught. And because my charge is positive, it points radially outwards. Okay, next, what if we're outside the cylinder? So my Q enclosed is still density times volume. But this time I have to do the volume of charge within my cylinder, which is only on the cylinder. So it's the volume of the cylinder, the insulating cylinder, within my Gaussian surface. So you got to be really careful you know what volume you're using here. So density times pi times r squared over L, because there's only charge on the insulator. There's no charge in that vacuum between the insulator and the Gaussian surface. Put it all together now. E times 2 pi r L equals rho pi r squared L over epsilon naught. E equals density. Let's see what cancels here. The pi's cancel and the lengths cancel. That's all the cancellation we've got going on there. Rho times r squared over 2 epsilon naught times r, and that's radially outwards. Just like we did with the sphere, we can draw a graph if we wish. So this axis is distance from the center, this axis is the electric field. Inside the cylinder, the field is proportional to the distance from the center, so that's linear. Outside it falls off as 1 over r, which is not as steep as 1 over r squared. And at the surface, the maximum value is E equals rho times r over 2 epsilon naught. And we get the same answer when we plug in r equals r, no matter which equation we use. Okay, that's our insulating cylinder. What if the cylinder was a conductor? So with our conducting cylinder, what we know is that all of the charge is free to move. Because it's free to move, it's all going to move to the surface of the conductor. Okay, I hope that's clear. It's a little bit hard to draw. So we can still apply Gauss's law. We'll do a Gaussian surface inside. This might have been a little easier if I hadn't tried a 3D drawing. And I can draw a Gaussian cylinder outside. The radius in each case will indicate with a lowercase r. Length in each case will be a lowercase l. We can use our exact same result that we did before for finding the flux. So my net electric flux is equal to E times 2 pi RL. So my Q enclosed, when I have the conducting cylinder and my Gaussian surface is inside, equals 0 because all of my charge is on the surface. So when I put that together with my Gauss's law, I get E times 2 pi RL equals 0 over epsilon naught, E equals 0. So the electric field inside the conductor equals 0. When my Gaussian surface is outside, my Q enclosed equals all of the charge same as what we had if it were on the insulator. Because I'm assuming I have exactly the same object, I've just made it out of a different material at this point. Same charge, same size, but now it's made out of a conducting material instead of an insulating material. So the charge on the insulator would have been the density times the volume, which is pi r squared L. So Q conductor equals Q insulator equals rho times pi r squared L. Okay, put this together. My net flux is E times 2 pi r L equals my net charge over epsilon naught. Solve for E. The pi's cancel, the L's cancel. Equals rho times r squared over 2 epsilon naught r, radially outwards of course, same as the insulator. So once you're outside of a charged object, it does not matter if it's a conductor or an insulator. If we were to draw a graph, we'd have the electric field inside equals 0, and the electric field outside falls off as 1 over r. Okay, now we've got our sphere and our cylinder reviewed. We're ready to do some new interesting 2055 stuff.